Hello students, in this week we will learn about regression, that what do we mean by regression, how regression is performed. So in all the modules which will be coming in this week, they will be related with regression. So let's go to our first module, and before that, let me share my screen. Yes. So why do we perform regression, or what do we mean by regression first? So often what happens in our daily life or in our experiments, or well, first I will close my video. Yes. So in our daily life or in our experiments or in some naturally occurring phenomena, we are interested um, in learning about a relationship between a set of variables. For example, age and weight of the students at IIT Gandhinagar. For example, just this is an example. Similarly, in terms of examples from chemistry or chemical engineering, relationship between the output and the temperature at which the reaction takes place. Magnitude of an earthquake and the level of ground shaking that earthquake produces, right? So our interest in learning such a relationship is mainly coming from the fact that we want to predict the other variable if we know the first variable or one of the variables as a function of one of the variables. For example, we want to predict weight as a function of age, or we want to predict the outcome of a reaction as a function of temperature, or we want to predict the ground shaking as a function of earth magnitude. So regression analysis is a statistical technique for investigating and modeling the relationship between two set of variables, or more than one variable. It can be two or three variables, for example, also. So the idea is that first we investigate about that what kind of relationship exists between these two set of variables. For example, we are discussing the cases here: age and weight, magnitude of an earthquake, and the level of ground shaking. And then we can make predictions based upon that learned relationship. So more often than not, what happens is that there is a single variable y. In many situations this happens, which depends upon the values of a input variable x. So we can define what is y and what is x. So in general, y is can be, though I'm taking it from those examples, y is weight, outcome, or the ground shaking. And the x will be age, temperature, and magnitude of an earthquake. So here we want to learn the relationship, or we want to investigate the relationship between y and x. So the simplest type of relationship between these two variables which we can think of can be a sort of linear relationship. Linear relationship means that the relationship between y and x can be explained by a straight line. So y is equal to alpha plus beta x is essentially a straight line. Or I can write this alpha as beta naught and beta 1 x. This alpha can be written as beta naught, and this relationship can be written as y is equal to beta naught plus beta 1 x. So in formal terms, in regression terminology or modeling terminology, y is the dependent variable, or we call it response variable, and x is independent variable or predictor or regressor variable. So you can make x as dependent variable or a y as regressor variable, but the usual way of doing things is like this, that y is often chosen as the dependent variable and x as the independent variable. So when I'm talking about these linear relationships, before we go next, I would like to add a caveat here that by using those examples which I have discussed in this slide here, by no means I'm suggesting that the relationship between weight and age, outcome of a temperature, and outcome of a reaction in the temperature, ground shaking of an earthquake, and the magnitude of an earthquake, that the relationship is linear. No, I'm not suggesting this. So I said that these are some cases where we may be interested in. These are some examples. So by using them as an example, I'm not suggesting that the relationship between them is always a linear. In certain values of age, temperature, or magnitude, it can be linear, right? However, one very famous example, which uh, I hope all of you know, is that a linear relationship that exists between voltage and current um, in a conductor. So if you apply voltage in a conductor and then measure the current, there is a linear relationship between voltage, applied voltage and current, if the temperature and other physical uh, factors are kept constant, and that is Ohm's law. So this relationship is a linear relationship, approximately linear relationship between voltage and current. This you know. So we are talking about such variables or such relationships. However, as you have noticed, that we are talking about the straight line behavior, but in practice, I will show you in one of the graphs in the next page that this relationship y is equal to beta naught plus beta 1 x is never ideal. Like it's never like that your all the observations are sitting over your straight line. So in fact, what will happen when I'm saying this, just for an example, that you may have different values of weights at the same age, right? Or if I say it, that you may have different values of current. Let's use the example current. I think voltage and current, because this is, you may have at same voltage different values of current. These different values of current, if you repeat the experiment time and again, these different values of current can come because of that, because the room temperature has changed or there are some other physical factors have changed, right? So because of some experimental error. So at a fixed value of x, if I'm talking about my voltage as x, you can have different values of y, right? So there is a scatter in y even at a single value of x. So that scatter in this equation is accounted by, or we add this scatter by writing this equation as y is equal to beta naught plus beta 1 x plus epsilon. This epsilon is accounting for the scatters in our observations. And this epsilon is a random error, or I can say it's a random variable. Actually, it's a normal random variable. It's a normal random variable. It's a normal random variable with zero mean and a variance sigma square. So this epsilon is accounting for the scatter even when we are measuring the value of y at a single x. So this is just an example, as I was discussing, that you can clearly see here, these are x values, these are y values. So I'm not naming what is x and what is y. The point which I want to discuss is that at one same value of x, you may have a scatter in y values. As you can see, you don't have the values of y that they are sitting over this straight line all the time. There is a spread in y values. This spread I'm talking about, this scatter in y we are talking about, and this spread is modeled by this epsilon, and we model it through that this error is coming from a standard normal distribution with a zero mean and standard deviation sigma. Now, as we have seen that at single x, we can have multiple values or we can have scattered values of y. Now, let's see what implication it has in terms of modeling or what impact it has on y. Let's see this in a little bit detail now. So we have our model y is equal to beta naught plus beta 1 x plus epsilon. Now, if I fix the value of x, so I'm fixing the value of voltage, for example, in voltage and current example, I'm fixing the value of voltage and then I'm measuring the current multiple times. Let's say it like this, that I'm fixing the voltage and after every 5 minutes, I'm measuring the current. So if you see, if I fix this x for a particular x, what will be the expectation of y? So I can write this y given x is in this form. So expectation of beta naught plus beta 1 x plus epsilon. I can take this expectation operator inside. So it will be expectation of beta naught, expectation of beta 1 x plus expectation of epsilon. You know that beta naught will be a constant. So we can write it as beta naught. Beta 1 is a constant, x we have fixed, so it's also a fixed constant. So we can write it beta 1 x because expectation of a constant is the constant. And we have just now said that expectation of epsilon is 0, so it will be 0. So that means expectation of y at a fixed x is beta naught plus beta 1 x. And the variance of this at the fixed x can be written as variance of beta naught plus beta 1 x plus epsilon. Variance of, I take variance operator inside, variance of beta naught, variance of beta 1 x plus variance of epsilon. And you know, these are fixed constants, so their variance will be 0. What we are left with is the variance of epsilon, which is sigma square. So it has two major implications now. First is that we said epsilon is a standard normal random variable. This automatically makes y also a random variable, a normal random variable. Rather, we say it normal random variable. However, the mean of y is not going to be 0. The mean of y will be this. The expectation will be this, and the variance will be sigma square. So it will have the variance as that of the epsilon, but mean will be beta naught plus beta 1 x. So now the implications of being epsilon being a normal random variable is that it makes y also a normal random variable at a particular x, at a given x, with a mean beta naught plus beta 1 x and with a variance sigma square. It has some more implications also, that at each observation, because here in this case we fixed x, right? So if I take another value of x, I fixed voltage at 5 volts, next time I make it 10 volts. So at each observation point or at each x, this y will be a random variable, normal random variable, where the mean of this will depend on beta naught plus beta 1 x, while the variance at each observation or at each x will just remain sigma square. So if I want to show this graphically, you can see it here. So here this is x-axis and here we have our dependent variable on the y-axis. So what do we mean by this? So the point is, or what I want to say here is that at a given x, at this value of x, your y values, which are along these, they are coming from, or they are being sampled from, let's call it like this. They are being sampled from a normal distribution which has a mean beta naught plus beta 1x, which depends upon the value of x, and a variance sigma square. And this variance does not depend upon the value of x. It's purely a random error because it's the variance of the error. Similarly, that means if I go to another value of x, for example, at this x also, the y is getting sampled from a normal random distribution with a mean again, this, and the variance sigma square. So that means that there is a distribution of y values at each x, and that the variance of this is distribution is same at each x, sigma square. Right? This is an important statement. Now, so we again formalize things here, and then we will go how we estimate beta naught and beta 1. So usually what happens, we first collect the data in terms of x and y. So we have paired data set, the independent variable and the dependent variable, for example, voltage and current. And often we assume that x is a controlled variable. So the analyst thinks that the x has been measured with negligible error. So there is no error in x. The error or the scatter is only in y. So y is the response variable, which is a random variable. So we are treating y as a random variable. Beta naught and beta 1 are the unknown coefficients. Sometimes they are called model parameters also. And epsilon is the random error. And finally, we make this statement again that y is a random variable with a probability distribution at each possible value of x, with beta naught plus beta 1 x as its expectation, its mean, and variance sigma square. I'm sorry. Now, estimation of beta naught and beta 1. So you have been given the data, paired observations like xi, yi, where I goes from 1 to n, the total number of observations. And you think that you have plotted a scatter plot, which we just discussed, and you want to determine this relationship. And in order to determine the relationship, you need to know the intercept and the slope of the straight line. So we can write this relationship for each observation as yi is equal to beta naught plus beta 1 xi plus epsilon I. Now there is one method to determine these values, which we call the sum of squares, method of least squares. That means we first compute sum of squares. This is a new term coming here, sum of squares. We will see what is it. What do we mean by sum of squares? So sum of squares is nothing but is the difference between your observation and the model. This is your model, this is your observation. And square it for each observation. So yi minus beta naught, beta 1 xi whole square, and sum it over all the observations. So this we call sum of squares. Now the method I'm talking about is the method of least squares. So I can write this, so you can see that essentially this sum of squares is sum of squared residuals, because epsilon is our error term, or we call it residual also sometime. So it is yi minus beta naught minus beta 1 xi, so is equal to epsilon I. So you can say it is least error. Let's not say it least error, let's just say it least square method. So, but the point here is that we can represent it like this also. Now, what do we mean by least squares? Or graphically, what is the sum of squares? So this is a straight lines. Suppose these are your observations. Again, we have variables x and y, a scatter plot, and then we are looking for a line such that which explains this variation very well. So I'm sorry that I have not drawn this line perfectly somewhere in the center, but it shows that we are looking for a line which is which minimizes the sum of squares. What do we mean by this? That this square distance, vertical distance between the observation and the line. So you can think of that there are n number of possible lines here that can pass through. There are n number of possible lines, but we are looking for the line which minimizes the sum of squares. That means we have to find beta naught and beta 1 in such a way that this sum of squares is minimized. So graphically, these sum of squares represent these distance. Graphically, this vertical distance between your observation and the line we are talking about. So there will be multiple such values of sum of squares for different lines, but we have to find the line for which this sum of squares is minimized. So in order to find this minimum, we differentiate the sum of squares with respect to beta naught and beta 1 and put them equal to 0, which will give us the values of beta naught and beta 1, which will minimize the sum of squares. So if first we differentiate it, partial derivatives with respect to beta naught, you can see that it will be all other terms are held constant. So it will be just with respect to this. So it will be minus 2 because it's a minus is here. So it will be minus 2 summation over I 1 to n yi minus beta naught cap beta 1 cap x. Now you must be thinking, I was earlier using beta naught and beta 1 and now suddenly I'm switching to beta naught cap and beta 1 cap. Yes, there is a catch here. So often we work with a sample of data. We don't get access to work with the population of data, the larger population. We don't have access to. Whenever we work with a sample of the data, a smaller sample of the data. For example, the voltage and current data you are working with, you are working on one day, but you do not have the entire population over all days, for example. Right? So you are working on a sample of the data. So the beta naught and beta 1, which we determine, they are determined from the sample. However, from those sample estimates, we want to make inferences, or we want to determine those values of beta naught and beta 1, which belong to the larger population. Right? So we say that beta naught cap and beta 1 cap are estimators of beta naught and beta 1. They are determined from the sample, but they are estimators for beta naught and beta 1 for the which belongs to the larger population. Which estimators? Because here we are determining beta naught cap and beta 1 cap from the least square estimates. So they are least square estimators. Least square estimators of beta naught and beta 1. So beta naught and beta 1, you can think of the coefficients of the so-called true model. What we think that the population, the data belongs to, or the relationship that explains the behavior of the larger population, right? So beta naught cap and beta 1 cap are just to distinguish them from the true values of beta naught and beta 1. So they are least square estimators of the actual values of beta naught and beta 1. Similarly, if we differentiate it with respect to beta 1, it becomes minus 2 epsilon summation over I 1 to n yi minus beta naught cap minus beta 1 cap xi. 1 xi will be there equal to 0. Now we rearrange the terms. You can see it will be this term. If we sum it over I equal to 1 to n, just we are summing a number or a constant n times. So it will be n beta naught cap plus beta 1 cap plus beta 1 cap summation over I 1 to n xi is equal to summation over I 1 to n yi. So we have taken yi on the other hand side. Similarly, from the second equation, beta naught cap summation over I1 to n xi plus beta 1 cap summation over I1 to n xi square. And then we take this term on the other side, so summation over I1 to n yi xi. So these equations are called least square normal equations, or sometimes just normal equations. So we will use these equations to estimate beta naught cap and beta 1 cap. So we have two equations and two unknown variables, so that is easy to solve. But before that, we defined the sample mean. As you know, sample mean for y values, so it will be y bar is equal to 1 by n summation over I1 to n yi. X bar, the sample mean for values of x, 1 by n summation over I1 to n xi. Then we write the first equation, n beta naught cap plus beta 1 cap summation over I1 to n xi is equal to summation over I1 to n yi. So beta naught cap will become 1 by n. So this term will go on the other hand side. So 1 by n, this n will come in the denominator. So 1 by n summation over I1 to n yi minus beta 1 cap summation over I1 to n xi. Using those definitions we just discussed, that summation 1 by n summation over I1 to n is nothing but y bar, and summation over 1 to summation over I1 to n xi divided by n is x bar. So beta naught will be y bar, beta naught cap will be y bar minus beta 1 cap x bar. We can replace this in this second equation to get this. So essentially we are trying to get now beta 1 cap. So if I replace it, we will find it here, y bar minus beta 1 cap x bar summation over I1 to n xi plus beta 1 cap summation over I1 to n xi square is equal to summation over I. So if sometime I'm not writing explicitly summation over I1 to n, it's implicit that the summation is going from I equal to 1 to the total number of observation, that is n. So sometime I'm writing it, sometime I'm not writing, but it is implicit. So summation over I 1 to n yi xi. Now if we further simplify this and use these definitions, that x bar will be 1 by n summation over I1 to n xi, and that means we can write this summation over I1 to n xi is equal to nx bar, right? So this we will replace here. So you can see that y bar minus beta 1 cap x bar, this term can be written as nx bar plus beta 1 summation over I1 to n xi square is equal to summation over I1 to n yi xi. Then we can take those terms which are associated with beta together. So beta 1 cap summation over I1 to n xi square, this term essentially, and the other term is this. So that will be minus nx bar square, and the other terms will go on the other hand side, that is summation over I1 to n yi xi minus nx bar y bar. So that gives us beta 1 cap is equal to summation over I1 to n yi xi minus nx bar y bar divided by summation over I xi square minus nx bar square. And this is our beta 1 cap. And we already know what is beta naught cap. So these values of beta naught and beta 1 which have come from the sample and using the least square method, so these are called least square estimators of beta naught and beta 1. Now you can clearly see here that I'm sorry, beta naught cap and beta 1 cap can be completely determined from the data. So as I said before, that we will be given data in the form of x and y like this, like a table. So if you are given the data, you can easily compute these terms here, whatever they are in the equation, you can sum it over, you can multiply each observation, cross multiplication, and then sum them over. You can compute those averages, and then you compute these terms also. That means, given the data, you can compute those values of beta naught and beta 1 cap, which will minimize the sum of squares, right? So that is how we determine the slope term and the intercept term of the linear relationship. In the next module, we will discuss some properties of beta naught and beta 1, because beta naught and beta 1 cap, they are determined from the sample, so they will vary from one sample to another sample, right? So we have to see what is their sampling distribution. Okay, so we will discuss very interesting properties of beta naught cap and beta 1 cap in the next module. So this module finishes here. Thank you.